Okay, welcome people of the pre-seminar. Our speaker is James Woodcock, and he's going to talk about something.
Okay, I'll announce that, I guess.
What's yours?
So for the pre-seminar, never given one of these before, I'm going to be talking about Poincaré duality.
This
is not very good, yeah.
Get it for the next one. Oh, three, no.
Okay. So, okay, I'm just going to assume some understanding of ordinary homology theory and Duran homology, just so I can get off the ground. So let's just write the practical statement. So we're going to fix M a closed and oriented manifold. Closed means compact and having no boundary. And we're going to denote the fundamental class like this. I guess it's an n-dimensional one. Then the homology of M is a ring. It has some sort of top product, and it acts on homology. It shifts the degree like so. You have a P form, and you have a Q cycle. Then you get out something in Q minus P. Q is okay. Very nice. Thank you. And the same with Poincaré duality is that H star, or the homology of M, is freely generated by fundamental class. Right, so the isomorphism of Poincaré duality is just kind of like an orbit map where you would just be moving everything around by the fundamental class with something in homology. Right? So, in particular, H star event goes to H and minus star. I take the cocycle and you pair it with your fundamental class. So this is an isomorphism, and this is going to be quite useful for sort of everything you do in geometry topology. So this is not the right one. This is okay. So in particular, we're going to get a perfect pairing, and we're going to do everything rationally now. So I'm just going to assume everything is rational coefficients. Of pairing from P n minus P and this P given by so if you have a P form and an n minus P form, then their wedge product is going to be a n form, and then you just measure that against this thing right here. And this is essentially how you would take the ordinary pairing between cycles and cocycles. But since we know how to make one the other, then you just make this a form, not a pairing. Right? Well, it's also a pairing nonetheless. So this will be very helpful. And this is a perfect pairing, meaning that it establishes an isomorphism between one and the base case of the other. Okay. So we're going to use this pairing to prove the Lefschetz theorem. We're going to talk about that, but first we're going to have to define what a trace sum map is. So you probably already know it's presented as a matrix what the trace is. You just add up the diagonal entries of your map. But so we're going to look more into characterization. So if we have a linear map like this, B is finite dimensional, and we have a perfect pairing V plus W. If you have a basis V and a dual basis for W, and this just means that the W is delta J. And so if you have a basis for one and you have a perfect pairing, you get a natural basis just by kind of evaluating your maps. Then the trace of T is given by the sum T. Yeah. I'm ready to solve this. So you can use any perfect pairing to compute trace. Right. So ordinarily, whenever you compute a trace, you would have you're looking at Rn, and then the dual basis for Rn is kind of well understood. You just raise the indices, and then this would just be something of each diagonal entry. Okay, so but this is helpful because we don't want to pick bases for everything, or when we do, we wanted to work for any pairing, like for this and this. So now we can use these things to compute traces, which is good. So okay, another consequence of Poincaré duality. This is an intersection product.
Yes, okay, a bit slow. Can you the corollary? So can you explain again what this is saying?
So if you take two forms on your manifold and you pair them together, you take a wedge card, right? Yeah. It has a natural multiplication, and then they're chosen so that their wedge will live in the nth cohomology, which means we'll pair with nth homology and give you a number. And nth homology is just the group generated by M. And so then you just pair this together, the canonical homology cohomology pairing. And you could define this whenever, like you don't technically need Poincaré duality to define this. You need an orientation to get a class like this. But this, I guess, would be an alternative way of presenting Poincaré duality, where this would give an isomorphism between this thing and then the dual space of this thing, but that is just homology once you picked rational coordinates.
And when you say multi-homology, the coefficients you're taking is in
the Q are usually the whole field. I think the statement is true over C, but to do stuff with pairings and the algebra, we're going to just pick in the field.
Okay.
Well, characteristic 0 problem. It was right. Yes. So since homology is a ring,
yes. So it's written definition position, right? Or what?
So sorry, what are we looking at?
It's definition and
Definition / correlation, right? This could be the definition of the trace.
what's the statement?
So if you know the definition of this is the trace of T, the proposition, I guess, would be that for any W you pick, and for any pairing you have, you would get this.
Okay.
So like the canonical choice, the one would be you let W be just a dual space of T. And then there the dual basis is obvious, and that's where you get your ordinary definition of a trace. So it just means the trace can be computed with any choice of a pair. Okay. Does that make sense?
Yeah.
Okay. Anything else?
Therefore, this is independent of the choice of the basis.
Yes. Yes, you could pick any other thing. And that's because like when you define your trace, right, one of the first things you prove is that the trace of S that's the trace of T. Right, and this just boils down to its basis independent. So. Can I use this if I don't wet it?
yes, absolutely.
Still scared. Okay. So cohomology is a ring. Homology is not a ring, but now we know it's isomorphic when we have this setup. So what is the ring structure you get whenever you just say, take two things in homology, put them in cohomology, multiply them, and then bring it back? Like, what is the ring structure you get out of that? And it's coming from a transversal theory. So if you have A and B submanifolds, let's say P dimensional, then we can have embeddings by definition. And so we can push forward their fundamental classes. These are the homology of it. So then this way we can think about the homology of a group being in some way sort of like algebraic combinations of submanifolds of your space. Right? So, and you take a submanifold, it's oriented, presume, and then you take it from into a class, and you just push that forward. And then we have this number. So when p plus q is equal to n, then a times b is a number which is going to live in 0 degree homology or homology. This is going to be equal to if we would take Poincaré to remove this thing, which this thing. So you can take your two submanifolds and you can make a product out of it. And this would just be there's a way you can do it just with Poincaré duality. This just exists formally, but you can also define it as what's called intersection number. And these things can be somewhat complicated, but essentially you take your two manifolds and assume that they sort of exist transversely to one another, that there's not coincidences along which they exist. And then you look at their intersection. And then these intersections will be weighted according to how they're put together, but essentially it's just the intersection of these two things is the resulting thing. But because of this property, their intersection is just going to be a finite set of points, right? Or generally. So the intersection of it is a weighted sum over finite intersection of a. Okay. So let's talk about a special case of this. So this is going to be a smooth map with finite fixed points. And we can make two natural submanifolds coming from the diagonal, which is just a collection of pairs, and the graph, which is the pairs with the value of the other one. These are going to be inside of n cross n. Okay, and these are both n-dimensional manifolds, so they're going to satisfy this sort of middle like property. And so we can do two things. Or we know from here that the fundamental class of this times the fundamental class of this thing is just some number. I guess. Yeah, it's just the time in the cube, but this is going to be an integer. And what this number is going to be under nice circumstances is it's going to be equal to the sum over the fixed points of x of sine of 1 minus, or the sine of the determinant, the 1 minus the differential of those fixed points. So I can't do this. This is just, this is something that people have done, and this is the main meat of the Lefschetz fixed point theorem, because this is a bunch of numbers ranging over the fixed point. So if the Lefschetz theorem will say that this is equal to the trace of the map on cohomology, and whenever you have a fixed point, wherever you have no fixed points, this thing is 0. So then the trace is 0, and vice versa. But this is not too hard to compute. It's essentially just like if you have a thing fixed at a point, if f fixes a point, and kind of around it, you can sort of treat it like you're mapping a disk into itself, and you can then take the degree of this one, and this degree will end up being this thing in nice pieces. That's all we're going to talk about. Okay, so how do you get the Lefschetz there? So, or Lefschetz fixed there. So if F holds non-zero trace. Homology. This is a super trace, so it's going to be written like F star. It's going to be some minus one to the trace F. And get out of the way frame.
Just close it so.
It's fine. So this is like a graded trace. On the even part, you have a positive contribution. On the odd part, you have a negative contribution. And essentially, you would show that the trace is equal to this thing right here. This intersection product is given by the trace. So you could make this a little fancy and say the trace is exactly this number right here, but in general, it is this number. But this sort of decomposition relies on no fixed points being sort of degenerate, where we erase this in a second. But if this is a fixed point, we can't have an axis around it where everything else is going into it, because then the resulting map that you look at around like an open disk will not be a homomorphism. You can't so cleanly talk about these things. But we don't need that whole again. So essentially just how it's done is we know that this thing right here is equal to something given in Coleman's right here. That would be P for the angle. Wedge. This thing. Right. And then we can show, which I'm going to hint at how this will work, that this sign right here gives you the trace of the map. Right? So essentially the concept of the theorem is this is the trace, and this is a weighted sum of fixed points. Right? So that's where the Lefschetz theorem comes from. And this will be appearing in the real talk process.
Give like 10 minutes left.
All right, good. And if I eventually I just roll over into the
Yeah.
Is that good or bad?
Start telling jokes.
You can start telling jokes, but we have to wait until 4 because you can break. And you can even go a bit longer because you start later.
Okay, well, that's not gonna be the problem. Okay, so how do you compute this thing? So some of the techniques that can be this are reminiscent of what is gonna be done for K theory. So first, you can write this as, I'll explain this as a right, so you pick a basis AI for homology, a homogeneous basis. So each of these has like a well-defined degree. And then we have a product on it, so then we pick a dual basis. And if this has dimension P, this has dimension N minus P. So whenever you sum all these things up, we're living in the dimension N, the middle dimension, which is what we want. And then this thing we represent, this is the Poincaré dual of that, because this is a cohomology. And the Poincaré dual of the graph, this is going to be equal to a similar thing. But instead of a little evaluate inside. And it seems like I have to erase it. So you really have kind of
You can move, you can flip that word.
really.
Yeah, keep going. Keep going. Don't say that. No, but it's
So I have to erase this too, though?
Yeah.
Okay.
Yeah, you put the last.
I'll put their writing stuff on there. I'll have to move all the junk off that thing.
This like this goes on.
Oh, no.
But then I'm covering every single thing. I'll just leave this open and it's okay. I will need to do this eventually. So you dip it.
Yeah.
And you scrub it. Okay. This is so crazy. I mean, how soggy do I get this thing? Everything like well,
Is the base.
Yeah.
You don't want to go ahead.
then squeeze that, okay.
It's like Yeah. Fine.
There you go.
Okay, I can see that.
Yeah, exactly.
All right.
Very natural.
Now the hardest part.
Then do I leave this in here, I assume?
Yeah.
I hope that just went in there. Is it, where's the water gonna go? Is it just gonna go on like?
Yes, this sponge, you put the sponge underneath, that's cool, man.
And that's next to that.
And the side to side or on the?
That's what I would decide.
Side to side. Voila.
Oh, that's beautiful. Very good technique.
Seems very extra.
I mean, but come on, compare this to the chalkboard Robin's office, it's always like. Got diamond levels of.
It has a history, it has a past. It's beautiful. But is it dry? It is. But is it dry enough?
Yes.
Okay.
It's only one way to.
Okay. What was I gonna do?
Let's see this.
Okay. So yeah, everything you need to know what we did. Importantly, we have kind of explicit descriptions of what these two classes are. And then we're just gonna be taking a product like this. But then the first sort of, I'm not the one to walk you through how this works, but you can deduce that, then rewrite this and this, how is it? I think we can consult it. Yeah, okay, where this map. Possible. And just go. And so you can reduce it to this. And then you would write out what this thing is, which is going to be this. Very awesome. The wedge for the tensor products become wedges, essentially. So we're essentially done, right? So recall here that you can take any dual thing and then just sort of measure your thing against it. So if you rewrite this. Then this is the sum. The trace. Essentially just because of this. Now it's on the wrong side. I put it in something wrong. But you can imagine that this is only wrong up to a side. You know, but it works. So this is pretty good news. You know, it's not too difficult to prove if you accept some sort of basic facts from geometry and topology. But it comes with it, like this sort of carries a lot of practical results. Now, if I proved the general statement for there's a similar statement for the simplicial finite simplicial complexes, but I didn't prove it, so I guess can't do it. But we have with it a lot of extra things. So this is called a Poincaré index theorem. So if X is a vector field on an vanishing and we find it in the points can be non-vanishing, I guess. Then the Euler characteristic of a manifold can be expressed as the sum of its local indices that's bad. Zero. And so a local index is very similar, it's just what you get whenever you. So you just like isolate your vector field, make an open disk around it, and then you take a degree map, right? So you're just looking at the map and uses some of the spheres sitting around it. And you always get the Euler characters. Now, what the Euler character is essentially just the trace of the identity map. You know, it's just the sum of the even dimensional cohomology and subtract off the odd dimensional cohomology. And that's just the trace when that is the identity. So you take your vector field, and in small time it'll do some map, which only fixes these finite points, and then you apply this theorem to it, and the trace will just be this, and then this takes on a recognizable form. Like if you come from differential equations, this is like something you would have seen before. So, and as a result of this, you have a hairy ball here. And the field. Plus 2 vanishes. Somewhat. And the proof. There you go. So because you can take the vector field as this thing right here, so you put 2 in, that means there's something on the right hand side. And then you're done. And you can even generalize this further. If n has a nowhere vector field, then zero. So this covers a lot of nice possible results. But it does go from. I'm going to talk about that in real time. I'm telling jokes now. It's like real.
Yes, so let's think that is sort of. We get some questions about the reason.
So can I ask in the statement of the Slashdot's term, the hypothesis that trace is non-zero?
Oh, did I not write it?
You did.
Oh, yeah.
My question is, if it has zero trace, what, this is not true?
So
or
it's fine. So you can have many fixed points, but the key is that it's like a weighted sum of the fixed points. So some can have negative weighted, some can be positive, so they can cancel out. I don't have an example off the top of my head, but you can take the zero trace. I mean, you could probably take a map on a sphere, a 2-sphere, which will tend, which is negatively oriented, has a degree -1, and then the trace will be 0. That still has a fixed point. Now, I don't know if you can easily make sense of that. That's what I would do. But it's complex to this. You have to know information about the fixed points themselves.
Maybe also one question about this theorem. So do you have something similar, let's say, for the intersection of 2 different of the graphs of 2 different functions?
Yeah, so this is called coincidence value theory, and there's a Lefko's theorem for that. But I think for that you end up sort of, it's not a simple trace, but it's like you would have one map going the correct way on cohomology, then you'd have a wrong way map, and then you would be maybe taking like a trace kind of thing whenever you compose the right way with the wrong way or the other one, something like this. But there is a fixed point formula or a coincidence value formula for which boils down to putting the identity as one of these things here. You would do the same thing but for 2 different graphs, which I guess I find to be points in on.
Now that I think about it, maybe you could take the take the difference and then simply take the fixed point of the difference, then it's maybe the same thing. I'm not sure. Yeah. Because here okay, it's not so.
I mean, that might just give you the ones which are fixed by both of them somehow. I don't remember exactly, but there's somewhat. Yeah.
Maybe one more question. So this half of this theorem is this Heinz-Hoff?
It's a good question. I think it's just how many Hoffs are there? Sorry, I don't know. It's the Hoff, I'm pretty sure. Yeah. It's the vibration guy. I don't know.
That's
The algebra guy, y'all like the algebra. So yeah. Heinz-Hoff was and I assume there's only one function. So probably that. So
With more questions?
No?
Could you explain again this formula P of investment data, like how confident is this?
So essentially, you would, so I don't know exactly where this formula came from. It comes from textbooks, to be fair. But how I like to think of it is like you would have a dual, you would have one form, which is in degree P, and then you'd have to complement it with the, the rest of it in degree N minus P. And then whenever you just tensor over all those things, you've chosen a basis, and you kind of given everything. I don't really know how to put it exactly, but the formulas like needs to appear all the time when you're doing Poincaré.
If the thing in the power of the -1 is partially.
Oh, that's just the degree. Like these are all weighted things. Like some are like a P form, you would put a P, and but all of them is just a sign. If it's 0 or 1, sign. But yeah.
I'm trying to remember back. There was so the Slesh's fixed point theorem, if I remember, is used if you go to algebraic geometry over what you use. This appears, and it appears in Bayes' proof of the
Violent conjectures.
Bayes conjectures.
Exactly. Yeah, and so he proved it in through sort of more categorical way, which I don't know if it was intentionally mimicked.
Andre.
Yes.
Yeah.
And then you could do the same thing for the category of C-star algebras. And that's how you get it. That's how you start talking about Lefschetz's theorems for C-star algebras. It essentially just boils down to, this was noticed by Heath Emerson, that all you need to prove it is you need a notion of Poincaré duality, and you need what's it called? What's the thing that tensor products? You need a Kuhn theorem. What was relied on heavily is that taking tensoring with Q still gives you rational homology and cohomology. It just that can't go wrong if you're doing things in other settings. Like for C algebras, it's not always true. You're doing K theory. So, yeah.
Because I remember the map that he was looking at for trace. That was the Frobenius map where you're rating the power of these finite field F so P. This automorphism.
I actually did not know what he did with it exactly. It
was Frobenius map.
What are the fixed points of the Frobenius map? Tell you.
I mean, it's related to the Bayes conjecture to like a realization function of somehow some of the fixed points he was getting, whether this could be understood in terms of the Frobenius data.
That's very interesting. You should know more about that stuff. So the point we bring up is if you do the same game in different contexts, the interpretation of this thing, you'll always have two sides. You'll have this side and you'll have this sort of cohomology. Yeah, I guess you really always have these two things. And this side will be some sort of weird geometric thing you have to compute. And this side will just give you the trace. Right. So then, when you do an algebraic geometry, you have to interpret what's going on this side. It's probably going to be a lot different than what's going on here. And so whenever we're doing this with C-star algebras, the computation of this side is actually the only hard part. This will just be an index pairing, which you have to interpret somehow. But filling now over time. Right.
Okay, do we have more questions? Maybe from online audience? Can you check just there is no question. Okay. This is James. Nice talking. Other than 8 minutes.